All right, good morning. Okay, let's continue on the lecture now, but we're going to temporarily change to a different kind of a topic now. Okay, so we have been dealing with a lot of issues with vectors or in vector fields. So we're going to temporarily get away from that, and we'll go back to the vector field and the vectors. We'll deal with integrals now. Okay, yeah. Particularly, we're going to deal with multiple integrals. So not just a single integral of a single function, single variables. We're going to deal with integrals of multivariables. So the first kind of integral we're going to look at today is called the double integral, okay. And then we'll look at the triple integral. Okay. Okay, as always, let's start from the simple one. Let's consider a function of single variables. So let's take a quick review on how integrals of function single variables was conducted. So if this is a function f of x at here, now if we're going to, let's say, calculate the area of this, the area underneath this curve at here. So how do we do that, right? So if you recall that, we can use this limit concept or approximation concept to get the approximate area of this underneath the curve at here. So this is A, this is B, okay. And we can pick anywhere in the middle. Let's say call it x of k at here. Okay. Then around the x of k, okay, so you have a delta xk. Suppose you have a delta xk segment around that location. Then we can always construct ourselves a rectangle, right, around that area. Then the small area, okay, associated with this location is the bottom length times the height, right? And the height, we can use the value of the function at x of k. So that will give you this rectangular area, okay, with this approximation. Then the total area is equal to, is approximately, okay, if you have many of this small rectangular area, then you add them up, you get the total approximated area. Let's just suppose we have n number of this rectangle here. So we get this approximation, right? Okay, very simple. We have been very familiar with this. But if I need the precise area, okay, underneath the curve, then we can let this number n go to infinite. And when the n goes to infinite, the summation sign will become integral sign. So the total area, the summation sign become integral sign, and all the delta here become straight d, right? So you get fx straight d, and integral will become a to b, right? So that gives you the total area here, right? That's sort of the idea how you integrate this f from a to b. Okay. Now, the other thing that I want you also at least for now to change this kind of to give a different type of thought is when we do this integral here, you can also think of what we're doing is we're doing a sweeping idea here. So when you're integrating from a to b, right, from a to b at here, then as if we're, let's say we have one straight line starting from the beginning, okay, then you sweep this straight line, okay, all the way from here to here. Okay, so it's like you're sweeping across this range a to b. Now the idea of integration is your sweeping has to cover every corner, right? Every corner, every area of this of this location here. So if you can do that, it's basically like when you're using a CAD software to generate, for example, a certain shape, right? If you, let's say, you want to generate a sphere, you can generate a half a circle first, and then you let the SolidWorks to sweep 360 degrees, right? Then you generate this solid sphere. So this one here very similar. So you can create a line first, then you sweep this line all the way from left to the right. The result of sweeping is to generating this shape, this area here. So that's basically another perspective you can understand how this integral is done. Sweeping from A to B to generate, okay, this area, to cover all this area here. Okay. So I'm going to use the very similar idea here to cover this double integral. Okay. To cover the double integral here. Okay, so let's take a look at this again here. We all understand if you have function here, the integral here give you the area underneath the curve. Now, if you only look at this integral, it doesn't necessarily is always an area concept, because it's a mathematical integral. You can actually have many other different applications here. Okay? Now, let's consider a double integral now. Given a function of two variables. And I'm going to draw this function over here. So here's a surface, right? As we all learned, when you have a function two variables, you end up with a surface. And at the same time, okay, we're going to have also be given a region R, okay, in XY plane at here. So there are basically two given conditions. Just like the function single variables, you have given this curve and you're given this range A to B. So here we're given this multivariable function f of xy, and then we have a region R at bottom here. So here is xy plane, and here is region R. Okay. So two things we're given in here. Right. So how do I formulate the problem now? So let's say right now we have a question, and here is, so we ask this question: what will be the volume below this surface and above the region R? Okay, so that's a legitimate question. You have a surface on the top and then a flat region at the bottom. Okay. So then what will be the volume between these two objects? Okay. And apparently if you want to calculate the volume, then all you need to do is you can, it's like you gonna create a cup or something. So from the bottom of the region and you go above, right? And you basically gonna create a solid, okay, and then you try to calculate the volume, okay, between these two boundaries. Okay, so that's the idea. Okay, but we want a precise calculation. I have a mathematical formulations calculation here. So I'm going to use exactly the same kind of logic for function single variables to illustrate how to calculate the volume here. So let's do this. Let's pick a point anywhere in the middle here. Okay, so anywhere in the middle, let's call it x of k. So pick this point here. Let's call it x of k, y of k. That's the coordinates of that point. And then I will create a very small rectangle, okay, around that location. And for this small rectangle here, the way you create it, basically you create it around the location, then one side, okay, let's say we call it delta yk, so there's a very small delta y change, okay, in the y-axis direction, and then the other side, let's call it delta x of k. Okay, so that's the how we create that small rectangle right here. Okay. So now I'm gonna extend this rectangle upwards, okay, until it meets the top surface f of x, y. So let's move up this rectangle here. Okay, this next doesn't matter, has to be very accurate, but as long as you understand the idea. Okay. Okay, so extend it up until it meets the top surface. So the top surface want to meet, when you sketch it out, doesn't necessarily it's going to be another rectangle anymore, right? But it's going to be a small patch on that surface f of x, y. So this is going to be a small patch there. Okay, so now I can formulate this question in here. So I can calculate what's the volume of this rectangular box. Okay. So what will be the volume of this rectangular box set here? It's a rectangle. Okay, it's not a perfect rectangle. So basically, bottom is here is rectangle, but then top here will be more or less a sort of a curved patch on the surface. Right? It's not a perfect rectangle box, technically speaking. But if this is a very small area that you picked, then on the top, right, it will also be very small. So you can approximate the whole thing as a rectangular box. The way to calculate rectangular box is the base area times the height, right? And the base area is delta xk times delta yk, and that's your base area. Okay, and the height. So with the height, we can consider this is a constant height because it's a very small area, and height we can use the value of the function at xk y of k. So basically, x of k, y of k, that it will be the height for this rectangular box. So if you go from this point upwards until the surface, okay, and that corresponding point on the surface is f of k, fx of k, and y of k. Okay, so that's the small volume of the rectangular box. Then apparently, if I'm going to do the same thing for many other different rectangular boxes, then I will get approximately the total volume. And that gives me a summation sign. Let's see if I have n number of them. So I'll get this approximation of the volume here. Okay. So we don't want the approximation as always. We want the precise. Then the only way to make it a precise total volume is we can let this total number of rectangular boxes n go to infinite. If n goes to infinite, as always, your delta sign becomes a straight differential format. Your delta yk becomes dy, okay, and the summation sign will become your summation sign will become integral sign here. Now, however, as you can see now, okay, as this n goes to infinite, and x becomes dx, y becomes dy at here. Okay, yeah. The integral, one integral sign won't be able to deal with two variables here now, right? So that's what is going to happen here is we're going to have two integral signs now. So one integral deal with one, and the other one will deal with the other one here, as we're going to see. Now, but as did here, you have integral limits a to b at here, right? So what should I do with the limits? So now this one, for now you can't decide yet. You have to have the actual region in order to decide the limits. However, whenever you have an integral here, a to b. So a to b at here means what? You're integrating over this region, over this range a to b, right? That basically what it means. That's a sweeping concept, sweep from a to b. So now here, what are we integrating over? We're integrating basically over this region R here. You see this rectangular box at the bottom here, right? It's limited within this green region R here. So we need a small subscript R at here to indicate this is where we're integrating with. So you're integrating this function basically. Sorry, there's a y here, not a key. We don't need the key anymore. So you're integrating this function over this region R at here. Okay? Yeah. So this is be our total volume at here. Okay? And then dx dy sometimes you can see the notation here because delta x times delta y give you the small area, the base area. Okay? So delta x times delta y gives the small base area. Then dx dy, we sometimes just call it small differential area, dA. So this is a differential area. So that's the notation. That's how double integral is derived here. Where is it from, essentially? Okay. Yeah. Now, and you can also put it down the whole in a limit format here. Basically, when n go to infinite, and that's your double integral, right? How double integral is derived. Okay. All right. So we're clear with double integral. Where is it from, right? But the question is always, how do we calculate double integral? That's the computation part. You can calculate double integral using limit concepts, just like a single integral. You can use limit concept to calculate, but this is always a very difficult process, right? So we need a more formal, more straightforward, basically, concept here. And then I'm going to use this loaf of bread, okay, to illustrate the idea of calculating double integral. Yeah. So here's what I'm going to do. If you look at this loaf of bread, and if I ask you, say, if you want to buy the biggest bread as possible, right? Then you have to calculate the volume to make your money right on the band there. So you know what to do now. So basically say, okay, so let's calculate the volume, and then you look at it. Let's say I'm going to consider the bottom of the loaf of bread as my region R. Okay? Yeah. And we're going to consider the top of the bread. Consider the top of the bread here, okay, as what? My surface z equal to f of x, y. Okay? Yeah. And you can place this loaf of bread within certain coordinate system, of course. So now the rest of the work is, let's calculate. And it just happened already cut into little pieces. So this is basically become a divide and conquer type of a task. So you can calculate the volume of each pieces, and then you add them up, then you get the total volume, right? Instead of using double integral, basically. Okay. So that's actually the idea of calculating this double integral at here now, right? So basically, we'll try to get the volume of each pieces, and then we'll get the total volume by adding up all the small volume of each pieces at here. Okay. So here's another, basically here I'm going to illustrate the idea, okay, how to calculate based on that the procedure. So first thing what we're going to do is we're going to calculate the volume of the slice of bread. Okay. So let's take a look at how we slice it. Okay, how we can simplify the situation here a little bit. Okay, so here is how you can do it. Let's say we're gonna cut it. Okay, basically like this, using a plane parallel to the ZY. So you create essentially cross section over here, right? So you get a cross section area, and then doesn't matter where you cut, you can cut it anywhere in the middle. Okay. So this is the location of the cut, X. And then we're gonna basically create a very small slice around that area. Okay, so that's how you can create a small slice around that area. And the small slice over here, let's call it dx. So it's so small, it's very thin piece, right? So infinitesimal small dx at here. Good. Then the volume of this slice will equal to basically the area of the slice here, the cross section. Okay, because it's so small, so we consider it's even cross section. We also consider equal area on both sides of the slice. So it's area slice time the thickness. Okay. All right, so that's the first step, right? You get the volume of a single slice here. And then next thing here is we need the volume of the total So this will be easy. So we just need to get use the volume of one slice at here, and then times the number of a slice. Okay, so that will give us the approximate value here. Okay, so concur and divide. So let's take a look at mathematically how to insert each one of the information into the two steps at here. Okay, so let's consider the step 1 again. Okay, this is the step 1 here. Okay. Yeah. Step 1 here requires the information of area of the slice. Okay, so what will be the area of the slice here, which is basically the shaded area over here. Okay. So to make it a little bit simpler to observe, I'm gonna essentially just look at it into this perspective. Okay, look into this perspective. This way you will see you have y-axis here and you have the z-axis over here. Okay, and then you will see a certain kind of a cross section. Okay, something like that. So see a certain cross section here. Good? Yeah, so that's what you see. Now, how do I label this cross section here, right? Now, first of all, the top curve, which is this curve here. Now, that curve is actually right on the surface, z equal to f of x, y, right? So this curve is on the surface. How that curve is generated is you did a straight cut at this location x at here. So as you can see, basically, along this cross section, all of the x value are actually being kept at what? As a constant, right? So if you go from here to here, they all have the same x value here. Okay, so basically at this location, doesn't matter where you cut, you have a constant x here. So the top curve, even though this is a curve, you can label it as z equal to f of x, y, because if this x here you actually considered is as a constant. Okay, so somewhere you did the cut somewhere at the x value, x equal to 2 or 3, it doesn't matter, right? So this curve, you plug x equal to a constant here, then you get a function z equal to f of y, right? So that's basically it's a curve here. Okay, so this is your top notation here. And then bottom here is what will be the limits basically for the cross section. Yeah. And limit of cross section, as you can see, it depends on what? It depends on the bottom boundary, right, for the region R here. So you got a boundary, one boundary over here, you got a boundary over here. Okay, there are two boundaries. Now these two boundaries not necessarily are two constants. They can be two curves, right, or two sophisticated curve could be. So we label this y mean, y max. Not necessarily this is a constant value. This can be two curves at here. So we call this as y mean, we call this as y max. Yeah. So there's a difference between specific and a general here, right? But when it comes to this cross section, it's a specific, but when it comes to general cut, it's general value. So that's the labeling for this cross section. Now I can calculate the area of this cross section now, right? Area of the cross section. And the area of the cross section, this essentially is like a function of single variables. What's the area beneath this curve at here? So I just need a single variable integral. And this integral here requires the lower limits, the higher limits, and the function we're integrating with. And now the variable, which is what? What variable are we integrating here? dy. Very good. Okay, so because you're integrating from here to here along the y-axis. Okay. So as we do this step at here, this is also crucial. What do we treat the x as? Treat the x as what? Constant, right? So this is how you did the cut here, right? You did the cut with a vertical plane that is parallel to the zy plane at here. So that guarantee that all the x values are constant. And I don't care where you do the cut, but at that location, all the x's values are constant here. So you're going to treat this as a constant. And this is where sometimes it'll play some tricks to your mind again. Yeah. So if you treat this x as constant, then this is a function of a single variable, and this is basically just a single integral here. Okay. Now, step number 2, right? Once you get the area of the slice, okay, what you do is you use the area of the slice. Okay, so that's the area of the slice at here. Right, this is the area of the slice. And I want to get the volume of this slice. What do? I use the area of the slice times the thickness of the slice, which is dx. So we times dx at here. So that's the area of the slice times the thicknesses of the slice. You got a dx at here. Good. And the last step is to get volume of the bread. Then volume of the bread is to add all the slices up. So summation is a concept of integration. Then over here, I'll skip step number 3. Is basically you add another integration sign, or it's a summation. Summing what? Summing all the volumes, okay, of the slices. So that's your integration for the x variable at here. So integration of the x variable basically means we're going to integrate, okay, from one end, okay, to the other end. Okay, depends on this region R. So that's how you see the labeling here. So find the minimum and the maximum of this x range at here. So that's your x mean and x max. Now you get the total volume, right? So this is your total volume in here. Okay. Yeah. So before we go anywhere further, okay, let's revisit these two integrals at here. So you essentially here we get our double integral. So the k, as you can see, is to determine the limits of these integrals, right? The limits of the integrals here. First, y min y max. As you can see, where's y min y max? Y min y max depends on these boundaries, okay, of the region R, and it's an arbitrary cut, right, across this spread. So y min y max, they are not constant, not necessarily constant. In some questions they are constant. Depends on the region R here, right? So here's my comments. First, this y min y max, okay, they are usually, okay, not constant, okay, and they are typically functions depending on this region R. And they are functions of x, functions of variable x, okay. So that's your y min and y max. Now what about x min x max? Okay, so the outer layer limits, integral limits. Now if you go back to the way how we're gonna adding up all the slices here, basically we add all the slices from one end to the other ends, okay, and that requires finding the limits, the extreme value of the x from one end to the other end. So that basically means what? Actually extreme. So from one end to the other, the x min x max, they have to be constants now. Okay, so that the x min x max are determined by wherever the edge of this bottom region R is, right? So these two values, okay, they are constants. Okay, these constants has to be found through this given region R, of course. And it totally makes sense, because why? Because if you think about it, right? If you want the volume, which of course at the end give you a scalar quantity, after the first integral, your y is gone, right? You end up with purely what? After first integral, this will give you a function of x here. Okay, so it will become, let's call it maybe g here. So they will give you this function of a new function which is purely x. And then the second integral is you want to get rid of x. You want to come up with a scalar quantity. So then your x cannot be a non-constant anymore. It has to be constant. So then you can end up with a scalar value, right, for this volume here. So that's why these two has to be constants. Okay. So this is essentially the idea of generating this double integral. But the key is to find the limits appropriately. All right. Now before we even show you an example of it here. So the way we do this divide and conquer is we did a slice or generating the slice by using the plane parallel to this what? To the z-y axis. Okay? Yeah. But if you're a different a chef, then you probably wanted to generate the slice differently. You may actually you can generate a slice what? Using the plane parallel to x and z planes. You could slice it like this. Okay, it's a little awkward, but you could slice it like that. Then you can use exactly the same approach, step 1, step 2, to calculate the volume, right? So in that particular case, okay, this is what we call a change of order. So you can have a different order of integration. Different order integration. So that basically means instead of integrating y at the beginning, and then you integrate x, okay, first. Now then, of course, then you need the x min, x max at here, and the y min and y max at here, right? So that's called a change of order. Now change of order, you also have to be careful. doesn't mean just simply change. You don't have to change the limits. For example, you find the limits for this order here, right? Y min y max, x min x max. And if you change the order, doesn't mean you just simply plugging this x min x max, y min y max from the previous order and directly over here. Okay, and that actually is not right. So as you can see, this x min this max won't be the same as this x min this max. Okay, because when you do the slice, for example, like this, your x min here, x min there, so they are not constant anymore. They are becoming functions of y. Okay, so that's the tricky part here when you do the order of integration, different order here. How do you find the appropriate limits has to be done separately. As a matter of fact, as you can see in some examples later, the order of integration often in time also matters. Some order doesn't work at all, but then the other order will work. So that's basically sometimes choose the right order will simplify your computation quite a bit. Okay. Let's take a look at the very simple example first, and then we'll look at another examples. Okay. So in this particular case, I have a function f of x y equal to 4 minus x minus y. And then I'm given a region as following. So x between 0 and 2, and y between 0 and 1. Let's say suppose we just want to know what's the volume below this z equal to 4 minus x minus y and above this region R. Okay. So the region, I say this is a simple example because this region is very simple here. So this is actually something from now on, there's another skill to help you. You probably will need to have the skill to help you understand questions properly. Basically is to graph out this surface on the top and also graph the region at the bottom here to illustrate and help you with the computation. In this case here, let's say I'll graph this region first. Okay, x is between 0 and 2, so this is 0 and this is 2. Y is between 0 and 1, so this is 0 and this is 1. Okay. And when you plot this whole region out, okay, you basically get a rectangular region, right, in the xy plane. So that's a simple region. Okay. All sides are basically constants, right? And the top is z equal to 4 minus x minus y. You don't have a computer, so you don't have the precise drawing, but you got to be able still to know, what does z equal to 4 minus x minus y represent in the 3D space? What does it represent? It's a plane, right? Yeah. So you can draw any planes you want on the top of the surface here. Now, because you're integrating over this region, so you don't have to draw a very large plane. You only need a plane basically on the top of this region R at here, right? So let's say I'll just arbitrarily draw a plane, okay, and which is right on the top of this region R. Okay, right on top of the region R here. Is that good? Yeah. Now you actually sometimes can, in this case, can have a relatively accurate drawing. So let me ask you this. You see this line here, right? This is the line basically of the intersection between the plane and what? And this xy plane. And this line is what? This is the intersection between the plane and the YZ plane. So when you have two planes intersecting each other, in this case you create a line here, right? You create a line. So what will be the line equation for this one and this one? Let's deal with this one here. What will be the line equation for this between the top plane 4 minus x minus y and the xz plane? How do I generate this line equation? So you have this top plane at here, and you have this plane, xz. What is xz plane, mathematically speaking? Y equal to 0, right? Y equal to 0. So now you have an intersection between this guy here and y equal to 0. So then what's the line equation here? Minus 0, and then equal to what? Z. Okay, very good, right? So you don't need the 0 right here. So that's your line equation, right? Z equal to 4 minus x. So if you want a little more precise drawing, you can try to plot this z equal to 4 minus x in this plane. So similar for this one here, what will be the line equation for this section here? So that's what? Z equal to 4 minus y. Is that good? Yeah. So that more or less can give you relatively, information, right? More accurate information for the top here. Okay. So now let's get back to the double integral. So we're integrating basically over this region R. Integrate this function, given function in here, okay, f of x, y. So that gives us a volume. And the question, of course, is to determine the limits. But the first question actually is to nail down the order of the integration. So let's suppose I'm going to do the dy first, okay, and then integrate this dx. Integrate dx. And you can certainly do the other order, okay? Yeah. And both should give you the same answer. If I do this first, if you recall the steps, so when you do this step here, the idea is to slice this, right? Basically to generate a slice, right? Anywhere between, okay, like this. So when you cut through this, generate a slice. For this particular region R, then what's good is really doesn't matter where you cut, right? Where you slice it. If you look at the bottom here, the y min and the y max, okay, this is the y min, y max, they're always the same. And y min is always 0 because it's inside here, and y max is always here, which is 1. So that gives you basically 0 to 1, right, for the y min and the y max. And then the second step of the integral is basically you sweep from one end of the bottom region R to the other end of the bottom region R. So that basically means sweeping from here to here. And that represents x min and x max, which is 0 to 2. Right. So that this way here, you do these two steps, as you can see. First step, what do? We generated this cross section here, right? And second step, we sweep this cross section from one end to the other end. So these two steps here completely generating this solid region in here, this solid objects, whatever you want to call it. Okay? Yeah. And that's essentially the volume here, the double integral we're looking for. Okay, so let's take a look at the calculation of the double integral, and this one should be very straightforward. You just have to calculate independently, and the first integral you treat x as a constant. So for the first integral you get a 4y minus xy minus 1/2 y squared, and then 0 to 1, and then dx. So plugging y between 0 and 1 here, you get 4 minus x minus 1/2, okay, dx. Okay. And this is single integral, very simple. You get a number 5. That's the volume, okay, between the top and the bottom region. So is that good? Yeah. Okay, so this one is simple, right? But a lot of times here, the bottom region R is not necessarily going to be a rectangular region. It's going to be some kind of irregular region. Okay, often in time, the region probably sandwiched between two different curves. So let's take a look at a more general, basically, approach for finding the limits, okay, based on the region R. I'm going to use an example, but also I'll just call it to summarize here. Okay, so let's call it. How do I find limits? Okay, based on the bounded, okay, non-rectangular region R. Okay, so more general region R. So here are the specific steps that involve it here. The first step, okay. The question will definitely describe the region R. So what you need to do is, if the question didn't sketch the region R for you, you need to sketch this region R. So that's this rough skill you need to have. Okay, not only just sketch it, okay, but also, okay, label the boundaries. So when region R is being given to you, you probably say, okay, region R is a region between this function and the other function. So when you sketch, you also label this you also label the boundaries. Okay, basically label the functions corresponding to the boundaries here. For example, right? We'll see region R is bounded by x squared plus y squared equal to 1 and x squared and x plus y equal to 1. Okay, so that's a very typical description of a region R. Okay, so in this case here, as we said, sketch the region R basically means involving the sketching of the two boundaries that are here. The first boundary is a circle, and the second boundary is a line. Right? So let's just sketch that in the xy plane. So you can sketch each one of them separately. Let's sketch x plus y equal to 1 first. So here's 1, here's 1, and that's your x plus y equal to 1. And then sketch this circle x squared plus y squared equal to 1. And this circle happens to pass these 2 points at here, right? So we can draw a circle, okay, passing through these 2 points. Since region R is bounded by these 2 functions, apparently the only possible region that can be bounded by these 2 is this part. Right? So that's how you can draw the region R here. Right? So in shots, you know, essentially at the end you don't have to draw this. You also just have to draw this, the half moon at here, right? This small ellipse. Good. Yeah. Okay. Well, as a matter of fact, it could be a possible. It's the bottom here, right? Could be a possible one here. So more precisely, maybe sometime we can add another condition. Let's say x greater than 0 and y greater than 0. So that'll limit to this region here. It's okay? Yeah. Okay. So the second thing is, now let's take a look at the general steps for finding the limits at here. Okay. So when you try to find, the second step is to deal with double integral now. And over here, the first step that you need to do is, you got to decide on the order of integration. Okay. So order of integration basically means, are we going to do dy dx or dx dy? Okay, so that basically here you're going to have two orders, okay? Dx dy or dy dx. So sometimes it doesn't matter, but sometimes really matters. So how do you tell? There's no trick at it here. So it's always just experience, or just trying and error. If one actually doesn't work very well, then you can try the other order, right? But in most of the cases that I have questions to give it to you, really it doesn't matter. Okay. So I'm going to use this dy dx as illustration. Okay. Illustration to find the boundaries. Okay, or the limits for the region R. So if I do dy dx, so that basically means we will try to find the y limits first. Okay, so try to find the y limits. I'm going to use that region R to illustrate the idea. Okay, so this is the region R. If you recall that this is x plus 1 equal to 1. Here is x squared plus y squared equal to 1. Okay. I'll use this to illustrate. How do we find this? Is here's the number of steps involved here. Okay, underneath small section. First, you draw an arrow, an arrow line, okay, across the region R, okay, in positive y-axis, okay, direction. So this is what you're going to do. Now this is an arbitrary sketch. So basically you draw it across here, so like that. Okay. Then you go along these arrow lines that you have just sketched. Okay, this is going to be a vertical line here. Okay, consider yourself, okay, just walking along it. Somewhere you will come across with this first, this is called a first contact, okay, with this region R. So I will have my first contact. The first contact, as you go along from the bottom to the top, the first contact give me the y mean. Okay. In this particular case, your first contact is the bottom line at here, right? Bottom line. So what will be my y mean? So anywhere, it doesn't matter where you draw the line here, you draw a line here, draw a line here. It's all the first contact is always the bottom line here. So the y mean at here, it's not going to be constant, right? Because you draw it here, here. So y mean changes. It depends on the bottom straight line. So y mean at here, what would that be? It's not 2, not 3, but it has to be something, right? 1. Huh? It's a function, right? So you draw it here, draw it here, right? It really doesn't matter, but there's got to be a certain values representing this first contact here.
1 minus x.
1 minus x, exactly, because that's the bottom straight line at here. Right? So it really doesn't matter where you draw this 1 minus x, this straight line here representing the y value. Okay, that's your first contact. And if you keep going at here, okay, and then you will go into this region. At a certain point, you're going to exit this region, and that's what we call the second contact. Okay. Second contact, that gives us the maximum limits for the so-called y max. And this y max in this particular region, as you can see, it's always on this outside circle curve. So now you can say what will be the expression for the y max, general expression for the y max now. It has to come out of this circle equation here. Right? And if you solve this, you get y equal to positive negative 1 minus x squared. So which one would you pick? Positive. Okay? Because you can't have negative in this particular first region in here. So there. So now this is your y mean, and this is your y max limit, okay, for the internal integral here, right? For this integral here, okay, this integral. Okay, so that's how you find the y limits. And the second step, okay, and under this small section here, is to find this x limit. X limits. Now, you can also consider basically for this first step here, when you go into first contact and the second contact, okay, literally what happens is you generated a small line segments from here to here, the green one. Okay, yeah. And the second step, finding the x limit, what you do is you're gonna sweep this arrow line, okay, across the region R, okay, from one end to the other end. So look at this case here. So when you're sweeping from one end to the other end, so that basically means this is one end at here, and that's another end at here. Right? That's how you can do the sweeping from one end to the other end. Okay. Then the x min, x max correspond to the value from one end to the other end. In this case here, it's very straightforward. So 1 and 0. In the other end, the x max is what? 1, right? Because that's the edge over there. So your x min is 0 and x max is 1. Okay, so then once you find all these limits, then the rest of the work becomes very simple, and all you need to do is just putting all the information into the missing puzzles here. So 0 to 1 for the x limits, and 1 minus x to 1 minus x squared, okay, for the internal y limit. Okay. So now you can, if you have the specific function given, then you can do the rest of the the integrals. Okay. Yeah. So that's how you can sweep through this region R, right? Sweeping through the region R, and without missing any corners, okay? Uniquely, and also without any redundancy. So here the idea is, so sweeping through region R, okay, sweeping through region R, and without redundancy. Okay. So you're not over sweeping it, you're not covering the same area twice, right? And that's basically integration. Uniquely sweeping through this region R. Okay. If I change the order of integration, for example, you know, this is dy dx. If I change the order of integration, then you can certainly try it out yourself. So let's say using the same region R right here, changing integration here. The first step, instead of drawing an arrow line this way, in the second, in this case here, you're going to draw an arrow line like this now. So this will become your first contact and the second contact. Okay. But you're integrating with respect to x first, and x will become y minus y squared, square root, and here, and then y is 0 to 1. Okay, so that will be the very similar, but it's a different orders though. Okay. All right, so let's take a look at a couple of examples, okay, to be more comfortable with the way to find limits, okay, for this type of a double integral. Okay. Region R is the boundary by y equal to x, x equal to 1, and x-axis. the function we're integrating with is 3 minus x minus y. Okay. So as I said, sketching out this region R is very important, which will help you immensely to how to find the proper limits, okay, based on region R. Some of them are very straightforward, very simple. This one is a simple one here. Okay. So let's take a look. So you have three boundaries for this one here. So y equal to x, x equal to 1, and then x-axis. Y equal to x, that's this one here. X equal to 1. So let's see, 1 is over here. So x equal to 1, that's another line here. And then x-axis, which is the bottom here. So altogether, you get this region R. Alright. Okay, so bottom line is we're trying to integrate this function through this region R. So first step, right, you choose the order of integration. For this one here, it really doesn't matter. So let me integrate y first, and then integrate the x next. So I'll give you 1 minute here to find out the limits by following that the steps illustrated above. So if you do y first and then x next, so follow at this stage, follow the steps precisely here, right? So what do? If you draw an arrow lines across the region, look at the first contact, second contact, which gives you y min, y max, and then you sweep the arrow line from one end to the other end across the region R to find x min and x max. Okay, so for this case, right, this is going to be your first step. This is the order of integration. So you draw an arrow lines across the region R in the positive x-axis direction. First contact, second contact. First contact is 0. Second contact, what would that be? X. Right. And then sweep these arrow lines from one end to the other end. That's according to the region R. Find the corresponding x min and x max. So in this case, 0 to 1. Okay. Yeah. And the rest of the work that I think in this case is very straightforward, because there's no trick at all, in this integral here, right? So 3y minus xy minus 1/2 y squared, 0 to x. Okay. So overall, I'm going to get a 1. Okay. The other thing I think also you notice that at this stage I didn't draw the function f of xy. I only draw the region R, right? But you in your mind, you also need to bear in mind is really what we're doing is it's in a 3D. This is x, this is y. This region, if I put everything in a 3D space, so this is x here, so this is your region R at the bottom here. And then that function z, 3 minus x minus y, it's somewhere basically on the top, right? Which is basically a plane. Okay? So that function f of xy is actually on top of this region R. So it's just that we didn't draw this the surface on the top. Okay. Let's take a look at a slightly different example here. Okay, slightly different example. Now this example here, you're given a double integral. Okay, so you're given a double integral right here. But you will be asked to do is, can you change the order? Okay. So change the order of integration. It's more or less like a reverse engineering, actually. So your change of order basically, instead of integrating dy dx, so you integrate dx dy. So no matter what, you need to find the limits, right? And finding the limits depends on the region R. But then this question didn't tell you the region R, only gave you the double integral. So the skill at here is, based on the given double integral, then you should be able to sketch out this region R. Okay, so that's what I call the reverse, sort of like reverse engineering. Okay. Okay, so what does that mean, right? So let's take a look at this. So the reverse engineering, so you gotta basically consider how these limits are generated, okay, when you're going over this order dx dy. The region R is there, it cannot change. And the limits are generated based on this order dy dx. So you just have to look at these limits carefully, okay, to generate this region R. So let's look at the limits here. So when you go, basically, remember the first step is you draw an arrow line in the y-axis direction, right? So you can imagine there's an arrow line here. That's the first step, isn't it, right? Yeah. When we draw this arrow line, the first contact give us y mean. So this is your y mean here. And the second contact give us the y max. So now I can try to draw the y mean, y max. So y mean equal to x squared. So that's my first contact. Or we just have to draw y equal to x squared. And that's a parabola, so you can draw this, which is y equal to x squared. That's your first contact. And then the second contact is y max equal to 2x. So you draw basically this is a straight line, y equal to 2x. Y equal to 2x, okay, will happen to be this one here. So now you can actually literally see the boundary got to be between these two curves. Right. So that's your region R. And then x mean, x max is when you sweep through this region R, right, sweeping these arrow lines from here to here. And this is 0, which is fine. Now here, is that going to be 2, right? So this is basically intersection between the two curves. And you can try to solve, of course, y equal to 2x, y equal to x squared, and you'll get x equal to 2. Right. So which happened to be 2, that's your x max, so which is perfectly okay. Once you find the region R, then change the order will become a relatively easy job now, right? So changing order basically means instead of drawing the arrow lines in the positive x-axis direction first, you draw the arrow line in the positive x-axis. Okay. So that's what change of order means. So dx dy, and if I look at this dx at here, so we will draw arrow lines, okay, in the positive x-axis first. First contact give me the x mean. Second contact give me the x max. First contact this time is on that straight line. Second contact is on that parabola. Okay. So what will be the x mean in this case? One over 2y. And what will be the x max then? Sorry, what's the one? X equal to 1 over 2y. Yes. Yeah. And x max is what? It depends on this curve here. Y equal to x squared. So x max is. Just a second here. What is it? Exactly. Yeah. Yeah. And then x max is square root of y, right? Yeah. because you're not gonna have negative number here, so this is all positive. So x equal to root y is your x max. Is that good? Then limits for the y is from lower limits here, which is 0 across it, okay, and then up to here. And that intersection for the y, basically the point over there is also 2, right? So actually, sorry, it's not 2. So when x equal to 2, the y value over there is equal to what? Equal to 4. Okay. So that's 0 to 4. So this coordinates at here is 2, 4. Okay. Is that clear? Yeah. So this is basically the idea of the double integral. It's actually, when you look at it, the whole thing for double integral is focused on finding the limits. As long as your limits is found properly, then the rest of the work is basically the scale of integral, right? Yeah. There's really nothing tricky here. And so far, actually, what I wanted to differentiate from the next one and cover is, so far what we have focused is basically what we call is the double integral, okay, in Cartesian coordinates. Okay, Cartesian coordinates. So this Cartesian coordinates is an idea, essentially is x and y, right? You know, you're dealing with x and y at here in a double integral. Now, to describe a point in 2D or 3D space, Cartesian coordinates is not only one, or not the only way to describe its position. So this is where I'm going to introduce you a different coordinate system. So let's look at the next one here. It's called polar coordinates. Okay, polar coordinates. So what is polar coordinates here? So let me illustrate this, okay, first. So let's say you have a location point P and you want to describe. And I give it the point P coordinates x, y. So that's what we call describe the location point P using Cartesian coordinates. All right? Yeah. However, I could actually use a different way to describe it. For example, if I create, let's say, a line or vector, no matter what you call it. Let's say if I connect the origin to that point P, and then I'll calculate the distance from origin to the point P. So I call it R. At the same time, I will look at the angle between that line and the positive x-axis. So two informations, right? The length from here to the point P and the angle between R and the positive x-axis. So this is actually important because in this case here, the x-axis is the reference. So you always start from x-axis and then going counterclockwise up to this R location. Okay, that gives me the theta angle here. So now you see, I can, instead of using x and y, I could also use r and theta, right, to describe this point P location. So this r and theta basically is called polar coordinates. Okay, polar coordinates. Now, what is called polar coordinates? You can also think of it like this. So I can establish a new coordinate system. So let's say this is I hat, j hat, right? So this is your xy coordinate system. I could certainly construct a new coordinate system like the way I'm going to show you here. Okay. I will let's say at this point here, I can create a unit x-axis direction okay, in this direction. This direction basically pointing, let's say if this is a vector, pointing to that vector direction. Here I will call it a unit vector ER hat. So this is just like the I hat. Okay, it's a unit vector, okay, representing that direction. At the same time, I can also create a perpendicular unit vector. Okay, we call it U theta E theta hat. This is like the counterpart of the J hat. So now you see here, it actually makes a lot of sense because ER, right, hat is the direction of the vector R. So if you have any point and you connect the origin to that point, then you certainly have a direction pointing to that direction, right? And E theta hat is actually pointing to the direction of the rotation, because you have a theta here. You know, the theta is essentially rotating around this vertical axis here. So E theta is perpendicular to the rotation here, which is also perpendicular to ER here. So that gives you a perfect like XY type of coordinate system, right? So this system here, you can call this is basically called polar coordinate system. However, the difference is, right, you see, XY coordinate system, it doesn't move, right? It's there. But if I change this point to different points, that coordinate system will actually what? Move to a different location. And not only move to a different location, there is some kind of a rotationing of that coordinate system. Does that make sense? Right? So that's the difference between these two at here, okay, between the two coordinate system. However, the R theta, right, really, that's actually a whole lot of different topic, you know. How do you describe the relative information between two coordinate frames? And this is the important part of the kinematics for robotics, basically, rotation, right, between two frames. And there's also translation between the two frames. So, but in terms of the coordinates, okay, for polar coordinates, you know, it's very simple, R and theta. Okay. And as a matter of fact, it's also very simple to establish connection between R theta and an XY here. So if you look at this, if this is X, okay, if this is Y at here, I can use very simple geometry. This is right triangle here, so I might get my X equal to R times cosine theta, and my Y equal to R times sine theta. Okay. Yeah. So that's the connection between polar coordinates and Cartesian coordinates. Okay, so very straightforward. Yeah. Polar coordinates are sometimes very useful to describe some very unique curves. Okay, so for example, I'll just quickly show you, and then we can just call it a day here. Some curves you can literally cannot describe using Cartesian coordinates, but you can describe using polar coordinates. There. So these are what I want to show you here. So for example, right, if you have an equation between R and theta like this, 1.5 minus 1.5 sine theta, you get a very beautiful cardial type of curve at here. Okay. You don't have this is a so simple description in R and theta, but if you write it in XY, it's much more complicated. Now if you change the theta to 3 theta here, instead of one paddle, then now you have 3 paddles here. So still a cardial, but 3 paddles. And you can change the magnitude, you can change the different number, then you have multiple ones here. So the application of polar coordinates has its own advantage in describing some unique curves or unique type of patterns, okay, in the plane. So I'm going to show you in the next lecture how to evaluate the double integral using polar coordinates in the next lecture. Okay? Any questions? All good? Okay.